We are here with a motto, and the motto this year is "Works for me." And I think, how many people in here are programmers? Raise your hands or shout or... Ooh, that's a lot. Okay. So I think many of you will work on x86. Yeah. And I think you assume that it works and that everything works as intended. And I mean, what could go wrong? Our next talk, the first one today, will be by Clementine Maurice, who previously was here with Rowhammer.js, something I would call scary, and Moritz Lipp, who has worked on the Armageddon exploit, bug? What is it? Okay, so the next, I would like to hear a really warm applause for our speakers for the talk. What could possibly go wrong with insert x86 instruction here? Thank you.
Well, thank you all for being here this morning. Yes, this is our talk, what could possibly go wrong with insert x86 instruction here. So just a few words about ourselves. So I'm Clementine Maurice. I got my PhD last year in computer science, and I'm now working as a postdoc at Graz University of Technology in Austria. You can reach me on Twitter or by email, but there's also, I think, lots of time before the Congress is over.
Hi, and my name is Moritz Lipp. I'm a PhD student at Graz University of Technology, and you can also reach me on Twitter or just after our talk and in the next days.
So about this talk. So the title says this is a talk about x86 instructions. But this is not a talk about software. Don't leave yet. I'm actually even assuming safe software, and the point that we want to make is that safe software does not mean safe execution. And we have information leakage because of the underlying hardware. And this is what we're going to talk about today. So we'll be talking about cache attacks. What are they? What can we do with that? And also special kind of cache attacks that we found this year. So doing cache attacks without memory accesses, and how to use that even to bypass kernel ASLR. So again, the talk says it's a talk about x86 instructions, but this is even more global than that. We can also mount these cache attacks on ARM and not only on x86. So some of the examples that you will see also applies to ARM. So today we'll have a bit of background, but actually most of the background will be along the lines, because this covers really a huge chunk of our research. And we'll see mainly 3 instructions. So move and how we can perform these cache attacks. What are they? The instruction clflush. So here we'll be doing cache attacks without any memory accesses. Then we'll see prefetch and how we can bypass kernel ASLR and lots of translations levels. And then there's even a bonus track, so this will be not our works, but even more instructions and even more attacks. Okay, so let's start with a bit of introduction. So we will be mainly focusing on Intel CPUs, and this is roughly in terms of cores and caches how it looks like today. So we have different levels of cores, different cores, so here 4 cores, and different levels of caches. So here usually we have 3 levels of caches. We have level 1 and level 2 that are private to each core, which means that core 0 can only access its level 1 and its level 2, and not level 1 and level 2 of, for example, core 3. And we have the last level cache. So here, if you can see the pointer. So this one is divided in slices. So we have as many slices as cores. So here, 4 slices. But all the slices are shared across core. So core 0 can access the whole last level cache, last 0, 1, 2, and 3. We also have a nice property on Intel CPUs, is that this level of cache is inclusive. And what it means is that everything that is contained in level 1 and level 2 will also be contained in the last level cache. And this will prove to be quite useful for cache attacks. So today we mostly have set associative caches. What it means is that we have data that is loaded in a specific set, and that depends only on its address. So we have some bits of the address that gives us the index, and that says, okay, the line is going to be loaded in this cache set. So this is a cache set. Then we have several ways per set. So here we have 4 ways. And the cache line is going to be loaded in a specific way, and that will only depend on the replacement policy and not on the address itself. So when you load a line into the cache, usually the cache is already full, and you have to make room for a new line. So this is where the replacement policy, this is what it does. It says, okay, I'm going to remove this line to make room for the next line. So for today, we're going to see only 3 instructions as I've been telling you. So the move instruction, it does a lot of things, but the aspect that we're interested about it that can access data in the main memory. We're going to see CL flush. What it does is that it removes a cache line from the cache, from the whole cache. And we're going to see prefetch. Here it prefetch a cache line for future use. So we're going to see what they do and the kind of side effect that they have and all the attacks that we can do with them. And that's basically all the assembly you need for today. So even if you're not an expert of x86, don't worry, it's not just slides full of assembly and stuff. Okay, so on to the first one.
So we will first start with the MOV instruction, and actually the first slide is full of code. However, as you can see, the MOV instruction is used to move data from registers to registers, from the main memory and back to the main memory. And as you can see, there are many moves you can use, but basically it's just to move data, and that's all we need to know. In addition, a lot of exceptions can occur. So we can assume that while those restrictions are so tight that nothing can go wrong when you just move data, because moving data is simple. However, while there are a lot of exceptions, the data that is accessed is always loaded into the cache. So data is in the cache, and this is transparent to the program that is running. However, there are side effects when you run these instructions, and we will see how they look like with the MOV instruction. So you probably all know that data can either be in CPU registers, in the different levels of the cache that Clementine showed to you earlier, in the main memory or on the disk. And depending on where the memory and the data is located, it needs a longer time to be loaded back to the CPU. And this is what we can see in this plot. So we try here to measure the access time of an address over and over again, assuming that when we access it more often, it is already stored in the cache. So around 70 cycles, most of the time, we can assume when we load an address and it takes 70 cycles, it's loaded into the cache. However, when we assume that the data is loaded from the main memory, we can clearly see that it needs a much longer time, like a bit more than 200 cycles. So depending when we measure the time it needs to take to load the address, we can say the data has been loaded to the cache, or the data is still located in the main memory. And this property is what we can exploit using cache attacks. So we measure the timing differences on memory accesses. And what an attacker does, he monitors the cache lines, but he has no way to know what's actually the content of the cache line. So we can only monitor that this cache line has been accessed and not what's actually stored in the cache line. And what you can do with this is you can implement covert channels. So you can allow 2 processes to communicate with each other, evading the permission system, what we'll see later on. In addition, you can also do side channel attacks. So you can spy with a malicious attacking application on benign processes. And you can use this to steal cryptographic keys or to spy on keystrokes. And basically, we have different types of cache attacks. And I want to explain the most popular one, the flush and reload attack, in the beginning. So on the left, you have the address space of the victim. And on the right, you have the address space of the attacker, who maps a shared library or an executable that the victim is used into his own address space, like the red rectangle. And this means that when this data is stored in the cache, it's cached for both processes. Now, the attacker can use the flush instruction to remove the data out of the cache, so it's not in the cache anymore, so it's also not cached for the victim. Now the attacker can schedule the victim, and if the victim decides, yeah, I need this data, it will be loaded back into the cache. And now the attacker can reload the data, measure the time, how long it took, and then decide, okay, the victim has accessed the data in the meantime, or the victim has not accessed the data in the meantime. And by that, you can spy if this address has been used. The second type of attack is called prime and probe, and it does not rely on the shared memory like the flush and reload attack, and it works as the following. So instead of mapping anything into its own address space, the attacker loads a lot of data into one cache line here and fills the cache. And now he again schedules the victim, and the schedule can access data that maps to the same cache set. So the cache set is used by the attacker and the victim at the same time. And now the attacker can start measuring the access time to the addresses he loaded into the cache before. And when he accesses an address that is still in the cache, it's faster, so he measures a lower time. And if it's not in the cache anymore, it has to be reloaded into the cache, so it takes a longer time. And he can sum this up and detect if the victim has loaded data into the cache as well. So the first thing we want to show you is what you can do with cache attacks is you can implement a covert channel. And this could be happening in the following scenario. So you install an app on your phone to watch your favorite images you take, to apply some filters, and in the end you don't know that it's malicious because the only permission it requires is to access your images, which makes sense. So you can easily install it without any fear. In addition, you want to know what the weather is outside, so you install a nice little weather widget, and the only permission it has is to access the internet, because it has to load the information from somewhere. So what happens if you're able to implement a covert channel between these two applications without any permissions and privileges so they can communicate with each other without using any mechanisms provided by the operating system, so it's hidden? It can happen that now the gallery image can send the image to the internet, which will be uploaded and exposed for everyone. So you maybe don't want to see the cat picture everywhere. And while we can use this with those prime and probe, flush and reload attacks, we will discuss a covert channel using prime and probe. So how can we transmit this data? So we need to transmit ones and zeros at some point. So the sender and the receiver agree on one cache set that they both use. And the receiver probes the set all the time. And when the sender wants to transmit a zero, he just does nothing. So the lines of the receiver are in the cache all the time, and he knows, okay, he's sending nothing, so it's a zero. On the other hand, if the sender wants to transmit a 1, he starts accessing addresses that map to the same cache set, so it will take a longer time for the receiver to access its addresses again, and he knows, okay, the sender just sent me a 1. And Clementine will show you what you can do with this covert channel.
So the really nice thing about prime and probe is that it has really low requirements. So it doesn't need any kind of shared memory. And for example, if you have two virtual machines, you could have some shared memory via memory deduplication. The thing is that it's highly insecure, so cloud providers like Amazon EC2, they disable that. Now we can still use prime and probe because it doesn't need this shared memory. Another problem with cache cover channel is that they are quite noisy. So you have other applications that are also running on the system. They are all competing for the cache, and they might evict some cache lines, especially if it's an application that is very memory intensive. And you also have noise due to the fact that the sender and the receiver might not be scheduled at the same time. So if you have your sender that sends all the things and the receiver is not scheduled, then some part of the transmission can get lost. So what we did is we tried to build an error-free cover channel. So we took care of this, all these noise issues by using some error detection to resynchronize the sender and the receiver. And then we use some error correction to correct the remaining errors. So we managed to have a completely error-free cover channel, even if you have a lot of noise. So let's say another virtual machine also on the machine serving files through a web server, also doing lots of memory-intensive tasks at the same time. And the cover channel stayed completely error-free and around 40 to 75 kilobytes per second, which is still quite a lot. All of this between virtual machines on Amazon EC2. And the really neat thing that we wanted to do something with that. And basically we managed to create an SSH connection really over the cache. So they don't have any network between them, but just they're sending the zeros and the ones, and we have an SSH connection between them. So you could say that cache, cover channel, nothing, but I think it's a real threat. And yeah, if you want to have more details about this work in particular, it will be published soon at NDSS. So the second application that we wanted to show you is that we can attack crypto with cache attacks. So in particular, we're going to show you an attack on AES and a special implementation of AES that uses T-table. So that's a fast software implementation because it uses some pre-computed lookup tables. So it's known to be vulnerable to sidechain attacks since 2006 by Osvik et al. And it's a one-round known plain text attack. So you have P, your plain text, and K, your secret key. And the AES algorithm, what it does is that it computes an intermediate state at each round R. And on the first round, the accessed table indices are just P XOR K. Now, it's a known plain text attack. What it means is that if you can recover the access table indices, you've also managed to recover the key because it's just a XOR. So that would be bad, right, if we could recover these access table indices. Well, we can with cache attacks. So we did that with flush and reload and with prom and probe. So on the x-axis, you have the plain text byte values. And on the y-axis, you have the addresses, which are essentially which T-table, the T-table entries. So a black cell means that we've monitored the cache line and we've seen a lot of cache hits. So this, basically the black area is the sure we are that the T-table entry has been accessed. And here it's a toy example, the key is all zeros, but you would have basically just a different pattern if the key was not all zeros. And as long as you can see this nice diagonal or a pattern, then you have recovered the key. So it's an old attack, 2006, it's been 10 years. Everything should be fixed by now. And you see where I'm going? It's not. So on Android, the bouncy castle implementation uses by default the T-table, so that's bad. And also many implementations that you can find online uses pre-computed values, so maybe be wary about these kind of attacks. The last application we wanted to show you is how we can spy on keystrokes. So for that, we will use flush and reload because it's a really fine-grained attack. We can see very precisely which cache line has been accessed. And a cache line is only 64 bytes, so it's really not a lot. And we're going to use that to spy on keystrokes. And we even have a small demo for you.
So what you can see on the screen, this is not on Intel x86, it's on a smartphone, on the Galaxy S6. But you can also apply these cache attacks there, so that's what we want to emphasize. So on the left, you see the screen, and on the right, we have connected the shell with no privileges and permissions, so it can basically be an app that you install from the App Store. And on the right, we are going to start our spy tool. And on the left, we just open the Messenger app. And whenever the user hits any key on the keyboard, our spy tool takes care of that and notices that. Also, if he presses the space bar, we can also measure that. If the user decides, okay, I want to delete the word because he changed his mind, we can also register if the user pressed the backspace button. So in the end, we can see exactly how long the words were the user typed into his phone without any permissions and privileges, which is bad. So enough about the MOV instruction. Let's head to CLFlush.
So this CLFlush instruction, what it does is that it invalidates from every level the cache line that contains the address that you pass to this instruction. So in itself, it's kind of bad because it enables the flush and reload attacks that we showed earlier. That was just flush, reload, and the flush part is done with CLFlush. But there's actually more to it. How wonderful. So there's a first timing leakage with it. So we're going to see that the CLFlush instruction has a different timing depending on whether the data that you pass to it is cached or not. So imagine you have a cache line that is on the level 1. With the inclusion property, it has to be also in the last level cache. Now this is quite convenient. And this is also why we have this inclusion property for performance reason on Intel CPUs. If you want to see if a line is present at all in the cache, you just have to look in the last level cache. So this is basically what the CLFlush instruction does. It goes to the last level cache, says, okay, there's a line. I'm going to flush this one. And then there's something that says, okay, the line is also present somewhere else. So then it flushes the line in level 1 and or level 2. So that's slow. Now, if you perform CLFlush on some data that is not cached, basically it does the same, goes to the last level cache, see that there's no line, and there can't be this data can't be anywhere else in the cache because it would be in the last level cache if it was anywhere. So it does nothing and it stopped there. So that's fast. So how exactly fast and slow am I talking about? So it's actually only a very few cycles. So we did these experiments on different microarchitectures, so Centibridge, Ivy Bridge, and Haswell. And so the different colors correspond to the different microarchitectures. So the first thing that is already kind of funny is that you can see that you can distinguish the microarchitecture quite nicely with this. But the real point is that you have really a difference. So the solid line is when we perform the measurement on CLFlush with the line that was already in the cache. And the dashed line is when the line was not in the cache. And in all microarchitectures, you can see that we can see a difference. It's only a few cycles. It's a bit noisy. So what could go wrong? Okay, so exploiting these few cycles, we still managed to perform a new cache attack that we call flush and flush. So I'm going to explain that to you. So basically everything that we could do with flush and reload, we can also do with flush and flush. We can perform cover channels and side channel attacks. Is stealthier than previous cache attacks. I'm going to go back on this one. And it's also faster than previous cache attacks. So how does it work exactly? So the principle is a bit similar to flush and reload. So we have the attacker and the victim that have some kind of shared memory, let's say a shared library. It will be shared in the cache. The attacker starts by flushing the cache line, then lets the victim perform whatever it does, let's say encryption. The victim will load some data into the cache automatically. And now the attacker wants to know again if the victim accessed this precise cache line, and instead of reloading it, is going to flush it again. And since we have this timing difference, depending on whether the data is in the cache or not, it gives us the same information as if we reloaded it, except it's way faster. So I talked about stealthiness. So the thing is that basically these cache attacks, and that also applies to Rowhammer, they are already stealth in themselves because there's no antivirus today that can detect them. But some people thought that we could detect them with performance counters, because they do a lot of cache misses and cache references that happen when the data is flushed and when you reaccess memory. Now, what we thought is that, but that's also not the only programs that do lots of cache misses and cache references. So we would like to have a slightly better metric. So these cache attacks, they have a very heavy activity on the cache, but they're also very particular because they are very short loops of code. If you take flush and reload, it's just flush one line, reload the line, and then again flush, reload. That's very short loop, and that creates a very low pressure on the instruction TLB, which is kind of particular for of cache attacks. So what we decided to do is normalizing the cache events, so the cache misses and cache references, by events that have to do with the instruction TLB. And there we could manage to detect cache attacks and row hammer without having false positives. So this is the metric that I'm going to use when I talk about stealthiness. So we started by creating a cover channel. First, we wanted to have it as fast as possible. So we created a protocol to evaluate all the kind of cache attack that we had, so flush and reload, and prime and probe. And we started with a packet size of 28. Doesn't really matter. We measured the capacity of our cover channel, and flush is around 500 kilobytes per second, whereas flush and reload was only 300 kilobytes per second. So flush is already quite an improvement on the speed. Then we measured the stealth. So at this speed, only flush was stealth. Another thing is that flush and reload, as you've seen, they shared some similarities. So for the cover channel, they also share the same sender, only the receiver is different. And for this one, the sender was not stealth for both of them. Anyway, if you want a fast cover channel, then just try flush. That works. Now, let's try to make it stealthy, completely stealthy, because if I have the standard that is not stealth, maybe that will give away the whole attack. So we said, okay, maybe if we just slow down all the attacks, then there will be less cache hits, cache misses, and then maybe all the attacks are actually stealthy. Why not? So we tried that. We slowed down everything. So flush and reload and flush are around 50 kilobytes per second now. Prime and probe is a bit slower because it takes more time to prime and probe, basically. But still, even with this slowdown, only flush has its receiver stealth. And we also managed to have the sender stealth now. So basically, whether you want a fast cover channel or a stealth cover channel, flush is really great. Now, we wanted to also evaluate if it wasn't too noisy to perform some side channel attacks. So we did these side channels on the AESD table implementation, the attacks that I've shown you earlier. So we computed the number of encryption that we needed to determine the upper 4 bits of a key byte. So here, the lower, the better the attack. And flush and reload is a bit better, so we need only 250 encryptions to recover these bits. But flush comes quite close with 350. And prime and probe is actually the most noisy of them all. Needs close to 5,000 encryptions. So we have around the same performance for flush and reload. Now let's evaluate the stealthiness again. So what we did here is we performed 256 million encryptions in a synchronous attack, so we really had the spy and the victim scheduled. And we evaluated the stealthiness of them all, and here only flush again is stealth. And while you can always slow down a cover channel, you actually can't really slow down a side channel, because in a real-life scenario, you're not going to say, hey, victim, wait for me a bit, trying to do an attack here. That won't work. So there's even more to it, but I will need, again, a bit of background before continuing. So I've shown you the different levels of caches, and here I'm going to focus more on the last level cache. So we have here our 4 slices. So this is the last level cache, and we have some bits of the address here that corresponds to the set. But more importantly, we need to know where, in which slice an address is going to be. And that is given by some bits of the set and the tag of the address that are passed into a hash function that says in which slice the line is going to be. Now the thing is that this hash function is undocumented by Intel. Wouldn't be fun otherwise. So we have this, as many slices as core, non-documented hash function that maps a physical address to a slice. And while it's actually a bit of a pain for attacks, it was not designed for security originally, but for performance, because you want all the access to be evenly distributed in the different slices for performance reasons. So the hash function basically it takes some bits of the physical address and output k bits of slice. So just 1 bit if you have a 2-core machine, 2 bits if you have a 4-core machine, and so on. Now let's go back to CLFlush, see what's the relation with that. So the thing that we noticed is that CLFlush is actually faster to reach a line on the local slice. So if you have, if you're flushing always one line and you run your program on core 0, core 1, core 2, and core 3, you will observe that one core in particular, when you run the program on one core, the CLFlush is faster. And so here this is on core 1, and you can see that core 0, 2, and 3, it's a bit slower. And here we can deduce that, so we run the program on core 1 and we flushed always the same line, and we can deduce that the line belonged to slice 1. And what we can do with that is that we can map physical address to slices. And that's one way to reverse engineer this addressing function that was not documented. Funnily enough, that's not the only way. What I did before that was using the performance counters to reverse engineer this function, but that's actually a whole other story, and if you want more detail on that, there's also an article on that.
So the next instruction we want to talk about is the prefetch instruction. And the prefetch instruction is used to tell the CPU, okay, please load the data I need later on into the cache if you have some time. And in the end, there are actually 6 different prefetch instructions. Prefetch T0 to T2, which means CPU, please load the data into the first level cache or in the last level cache, whatever you want to use. But we spare you the details because it's not so interesting in the end. However, what's more interesting is when we take a look at the Intel manual and what it says there. So using the prefetch instruction is recommended only if data does not fit in the cache. So you can tell the CPU, please load the data I want to stream into the cache so it's more performant. Use of software prefetch should be limited to memory addresses that are managed or owned within the application context. So one might wonder what happens if this address is not managed by myself. Sounds interesting. Prefetching to addresses that are not mapped to physical pages can experience non-deterministic performance penalty. For example, specifying a null pointer as an address for prefetch can cause long delays. So we don't want to do that because our program will be slow. So let's take a look what they mean with non-deterministic performance penalty. Because we want to write good software, right? But before that, we have to take a look at a little bit more background information to understand the attacks. So on modern operating systems, every application has its own virtual address space. So at some point, the CPU needs to translate these addresses to the physical addresses actually in the DRAM. And for that, we have this very complex looking data structure. So we have a 48-bit virtual address, and some of those bits map to a table, like the PM level 4 table with 512 entries. So depending on those bits, the CPU knows at which line he has to look. And if there is data there, because the address is mapped, he can proceed and look at the page directory, pointer table, and so on for the town. So everything is the same for each level until you come to your page table where you have 4 kilobyte pages. So it's in the end not that complicated, but it's a bit confusing because you want to know a physical address, so you have to look it up somewhere in the main memory with physical addresses to translate your virtual addresses. And if you have to go through all those levels, it needs a long time. So we can do better than that, and that's why Intel introduced additional caches also for all of those levels. So if he wants to translate an address, you take a look at the ITLB and for instructions and the data TLB for data. If it's there, you can stop. Otherwise, you go down all those levels. And if it's not in any cache, you have to look it up in the DRAM. In addition, the address space you have is shared because you have, on the one hand, the user memory, and on the other hand, you have mapped the kernel for convenience and performance also in the address space. And if your user program wants to access some kernel functionality like reading a file, it will switch to the kernel memory, there's a privilege escalation, and then you can read the file, and so on. So that's it. However, you have drivers in the kernel, and if you know the addresses of those drivers, you can do code reuse attacks. And as a countermeasure, they introduced address space layered randomization also for the kernel. And this means that when you have your program running, the kernel is mapped at one address. And if you reboot the machine, it's not on the same address anymore, but somewhere else. So if there is a way to find out at which address the kernel is loaded, you have circumvented this countermeasure and defeated kernel address space layered randomization. So this would be nice for some attacks. In addition, there's also the kernel direct physical map. And what does this mean? So it's implemented on many operating systems like OS X, Linux, also on the Xen, Hypervisor and BSD, but not on Windows. But what it means is that the complete physical memory is mapped in additionally in the kernel memory at a fixed offset. So for every page that is mapped in the user space, there's something like a twin page in the kernel memory, which you can't access because it's in the kernel memory. However, we will need that later, because now we go back to prefetch and see what we can do with that. So prefetch is not a usual instruction, because it just tells the CPU, I might need that data later on. If you have time, load it for me. If not, the CPU can ignore it because it's busy with other stuff. So there's no necessity that this instruction is really executed, but most of the time it is. And a nice, interesting thing is that it generates no faults. So whatever you pass to this instruction, your program won't crash. And it does not check any privileges. So I can also pass a kernel address to it, and it won't say, no, stop, you accessed an address that you are not allowed to access, so I crash. It just continues, which is nice. The second interesting thing is that the operand is a virtual address. So every time you execute this instruction, the CPU has to go and check, okay, what physical address does this virtual address correspond to? So it has to do the lookup with all those tables we've seen earlier. And as you probably have guessed already, the execution time varies also for the prefetch instruction. And we will see later on what we can do with that. So let's get back to the direct physical map. Because we can create an oracle for address translation. So we can find out what physical address belongs to the virtual address. Because nowadays you don't want that the user to know, because you can craft nice rowhammer attacks with that information and more advanced cache attacks, so you restrict this information to the user. But let's check if we find a way to still get this information. So as I've told you earlier, if you have a page in the user space mapped, you have the twin page in the kernel space. And if it's cached for both of them again. So the attack now works as the following. From the attacker, you flush your user space page. So it's not in the cache also for the kernel memory. And then you call prefetch on the address of the kernel, because as I told you, you still can do that because it doesn't create any faults. So you tell the CPU, please load me this data into the cache, even if I don't have access to this data normally. And if we now measure on our user space page the address again, and we measure a cache hit, because it has been loaded by the CPU into the cache, we know exactly at which position, since we passed the address to the function, this address corresponds to. And because this is at a fixed offset, we can just do a simple subtraction and know the physical address again. So we have a nice way to find physical addresses for virtual addresses. And in practice, this looks like this following plot. So it's pretty simple, because we just do this for every address, and at some point we measure a cache hit. So there's a huge difference. And exactly at this point, we know this physical address corresponds to our virtual address. The second thing is that we can exploit the timing differences it needs for the prefetch instruction. Because, as I told you, when you go down these cache levels, at some point you see it's here or it's not here, so it can abort early. And with that, we can know exactly when the prefetch instruction aborted and know how the pages are mapped into the address space. So the timing depends on where the translation stops. And using those two properties and those information, we can do the following. On the one hand, we can build variants of cache attacks. So instead of flush and reload, we can do flush and prefetch, for instance. We can also use prefetch to mount row hammer attacks on privileged addresses, because it doesn't do any faults when we pass those addresses, and it works as well. In addition, we can use it to recover the translation levels of a process, which you could do earlier with the page map file, but as I told you, it's now privileged, so you don't have access to that. And by doing that, you can bypass address space layout randomization. In addition, as I told you, you can translate virtual addresses to physical addresses, which is now also privileged with the page map file, and using that, it re-enables return to direct exploits, which have been demonstrated last year. On top of that, we can also use this to locate kernel drivers, as I told you. It would be nice if we can circumvent KSLR as well. And I will show you now how this is possible. So with the first oracle, we find out all the pages that are mapped. And for each of those pages, we evict the translation caches. And we can do that by either calling sleep, which schedules another program, or access just a large memory buffer. Then we perform a syscall to the driver. So there's code of the driver executed and loaded into the cache. And then we just measure the time prefetch takes on this address. And in the end, the fastest average access time is the driver page. So we can mount this attack on Windows 10 in less than 12 seconds. So we can defeat KSLR in less than 12 seconds, which is very nice. And in practice, the measurements looks like the following. So we have a lot of long measurements, and at some point you have a low one, and you know exactly that this driver region and address the driver is located, and you can mount those threads to direct attacks again. However, that's not everything, because there are more instructions in Intel.
Yeah, so the following is not our work, but we thought that would be interesting because it's basically more instructions, more attacks, more fun. So there's the RDSeed instruction. What it does is that it requests a random seed to the hardware random number generator. So the thing is that there is the fixed number of pre-computed random bits, and that takes time to regenerate them. So as everything that takes time, you can create a cover channel with that. There's also fadd and fmal, which are floating point operations. Here, the running time of this instruction depends on the operands. Some people manage to bypass Firefox time origin policy with an SVG filter timing attack with that. There's also the jump instructions. So in modern CPUs, you have branch prediction and branch target prediction. With that, it's actually been studied a lot. You can create cover channel, you can do sidechain attacks on crypto, you can also bypass kernel ASLR. And finally, there are TSX instructions, which is an extension for hardware transactional memory support, which has also been used to bypass kernel ASLR. So in case you're not sure kernel ASLR is dead, you have lots of different things to read. Okay, so on the conclusion now. So have you seen it's actually more a problem of CPU design than really the instruction set architecture? The thing is that all these issues are really hard to patch. They are all linked to performance optimizations, and we are not getting rid of performance optimization. That's basically a trade-off between performance and security, and performance seems to always win. There has been some propositions against cache attacks to, let's say, remove the CL1 instructions. The thing is that all this quick fix won't work because we always find new ways to do the same thing without these precise instructions. And also we keep finding new instructions that leak information. So it's really, let's say, quite a big topic that we have to fix this. So thank you very much for your attention. If you have any questions, we'd be happy to answer them.
Okay. Thank you very much again for your talk. And now we will have a Q&A, and we have, I think, about 15 minutes. So you can start lining up behind the microphones. They are in the gangways in the middle. Except, I think, that one. Oh, no, it's back up, so it will work. And while we wait, I think we will take questions from our signal angel, if there are any. Okay, there aren't any, so microphone questions. I think you in front.
Hi. Can you hear me?
Try again.
Okay, can you hear me now? Okay. Yeah, I'd like to know what exactly was your stealthiness metric? Was it that you can't distinguish it from a normal process, or?
So,
wait a second. We have still Q&A. Could you quiet down a bit? That would be nice.
So the question was about the stealthiness metric. Basically, we used the metric with the cache misses and cache references normalized by the instruction TLB events, and we just found a threshold under which pretty much every benign application was below this, and Rowhammer and cache attacks were after that. So we fixed the threshold, basically.
That microphone?
Hello, thanks for your talk. It was great. First question, did you inform Intel before doing this talk?
Nope.
Okay. And the second question, what's your future plans?
Sorry?
What's your future plans?
Future plans. Well, what I did that is interesting is that we keep finding these more or less by accident or manually, so having a good idea of what's the attack surface here would be a good thing, and doing that automatically would be even better.
Great, thanks.
Okay, the microphone in the back over there, the guy in white.
Hi. One question, if you have like a daemon that randomly invalidates some cache lines, would that be a better countermeasure than disabling the cache?
What was the question?
If invalidating cache lines would be better than disabling the whole cache. So
if you know which cache lines have been accessed by the process, you can invalidate those cache lines before you swap those processes. But it's also a trade-off between performance. Like, you can also, if you switch processes, flush the whole cache. And then it's empty, and then you don't see any activity anymore. But there's also the trade-off of performance with this.
Okay, maybe a second question. There are some ARM architectures that have random cache line invalidations. Did you try those? If you can establish a channel there?
If they're truly random, but probably you just have to make more measurements, and then you can average out the noise, and then you can do these attacks again. It's like with prime and probe, where you need more measurements because it's much more noisy. So in the end, you will just need much more measurements.
So on ARM, it's supposed to be pseudo-random. At least it's what in the manual, but we actually found nice ways to evict cache lines that we really wanted to evict. So it's not actually that pseudo-random. So even, let's say if something is truly random, it might be nice, but then it's also quite complicated to implement. I mean, you probably don't want a random number generator just for the cache.
Okay, thanks.
Okay, and then the three guys here in the microphone in the front.
Hello. My question is about a detail with the keylogger. You could distinguish between space, backspace, and alphabet, which is quite interesting, but could you also figure out the specific keys that were pressed? And if so, how?
Yeah, that depends on the implementation of the keyboard. But what we did, we used the Android stock keyboard, which is shipped with the Samsung, so it's pre-installed. And if you have a table somewhere in your code which says, okay, if you press this exact location or this image, it's an A, or it's an B, then you can also do a more sophisticated attack. So if you find any functions or data in the code which directly tells you, okay, this is this character, you can also spy on the actual key characters on the keyboard.
Thank you.
Hi, thank you for your talk. My first question is, what can we actually do now to mitigate this kind of attack by, for example, switching off TSX or using ECC RAM?
So I think the very important thing to protect would be like crypto. And the good thing is that today we know how to build crypto that is resisting to such an attack. So the good thing would be to stop employing implementations that are known to be vulnerable for 10 years. Then things like keystrokes is way harder to protect. So let's say crypto is manageable, the whole system is clearly another problem. And you can have different types of countermeasure on the hardware side, but that would mean that Intel and ARM actually want to fix that, and that they know how to fix that. I don't even know how to fix that in hardware. Then on the system side, if you prevent some kind of memory sharing, you don't have flush and reload anymore, and prime and probe is much more noisier. Much more noisy, so it would be an improvement.
Thank you.
Do we have Signal Angel questions? No. Okay, then more microphone.
Hi, thank you. I wanted to ask about the way you established the side channel between the two processes, because it would obviously have to be timed in a way to transmit information between one process to the other. Is there anywhere that you documented the whole, it's actually almost like the 7 layers or something like that? Is there any ways that you documented that? It would be really interesting to know how it worked.
You can find this information in the paper because there are several papers on covered channels using that. So the NDSS paper is published in February, I guess. Yeah. But the Armageddon paper also includes a covered channel, and you can find more information about how the packets look like and how the synchronization works in the paper.
Thank you.
One last question.
Yeah. Hi. You mentioned that you used Oswik's attack for the AES side channel attack. Did you solve the AES round detection, and is it different to some scheduler manipulation?
So on this one, I think we only did some synchronous attacks, so we already knew when the victim is going to be scheduled, and we didn't have anything to do with schedulers.
All right. Thank you.
Are there any more questions? No, I don't see anyone. Then, thank you very much again to our speakers.